Greetings. Welcome to week 4 of operating systems. Today, we're going to be talking about I/O device and I/O management. We've talked about processes. We've talked about memory. Now we're getting ready to go into the devices and I/O management. Things we're going to be covering today is device management fundamentals, I/O hardware components, interrupts and polling, direct memory access, device drivers, buffers, caching, and spooling, and disk scheduling algorithms. Those are the areas we're going to be covering today. Okay, so let's look at device management fundamentals. The operating system coordinates and controls hardware devices to provide efficient and reliable access to applications. Okay, so hardware devices, physical components that perform tasks. They include CPU, memory, usage, I/O devices. We're talking about the physical piece of equipment that's basically being used and being called on by your program through the operating system. So we got hardware devices, we got device controllers, interfaces between devices and operating system management device, operations and status, device interfaces, standard methods of communication, and provide uniform access. Okay, one thing that will be on the quiz, this is kind of a preparation, device controllers and device interfaces. Look up the difference and know the difference between the controller part of it and the interface part of it. Okay, resource allocation, the operating system schedules, allocates devices, and assures fair, efficient usage, kind of spreading the wealth across all the hardware devices are connected to the operating system. As far as the I/O hardware components, here you see we have keyboards, we got mouse. I/O components allow the system to exchange data with the outside world. They include input, output, storage, communication devices. Okay. Input devices sends data to the system. That's where we're bringing things into the operating system, in the memory, so that our program can actually and use it. Output devices present data from the system. We're pushing things out. Input devices, output devices, we're pushing out. Storage devices, storage data for future use. Examples: HDD, STD, optical drives, USB. Okay. Those are the type of anything that basically stores information and saves it will fall in that category of storage devices. Communication devices enable system communication. Examples: network cards, modems, Bluetooth, anything that has talking about moving data across some space of distance. Okay, next we have interrupts and polling. Okay, interrupts and polling, the operating system must determine when a device needs attention. So if I'm a printer, and you might have seen this before, and you run out of paper, okay, well, the printer sends a signal to the operating system, say, hey, something's wrong. So what interrupts and polling says, what are the ways that I can intercept that need for the printer to know that I have to do something? Okay, they want the operating system to do something. So that's what we're talking about here. How do we get notification that something's happened and then we need attention? So here, the operating system must determine when a device needs attention. It uses interrupts for immediate notification or polling to check the status at certain intervals. Every 30 seconds, I'm going to poll all my physical devices to see if everything's still okay. Okay, so interrupt-driven I/O devices signals the CPU when it needs service, faster response, better CPU. Polling, okay, interrupt is immediate. Okay, polling is, again, I'm just circling around And every once in a while, I'll check to see if there's anything needed. And that's basically on polling each device. Are you okay? Are you okay? Are you okay? That's the polling part. Well, operating systems repeatedly checks device status. Simple, but wastes a lot of CPU cycles, and that this is continuous. Excuse me. Interrupt handlers. Special routines that run when an interrupt occurs. So I have an interruption. I'm going to run this special interrupt program that's going to basically capture what the problem is, notify the operating system, and you see it on the screen. Okay, interrupt handlers. And then performance comparison. Interrupts on more that are more efficient and are scheduled. Polling may be used for simple devices. Okay, so looking at how polling and interrupts kind of compare with each other, it's just saying it's more efficient for me to do an interrupt, and I'm basically only sending at the time I need help, versus a poll, which is a continuous check. So performance-wise, interrupts are better, more effective than the polling. Then we have direct access management. DMA allows for data to be transferred directly between I/O devices and memory without CPU intervention. So this is good. This is where I have a physical device, and I say I'm an input device. So I'll take that input, I'll put it in the memory, but I don't need the central processing unit to do anything. I basically have the authority as being a DMA that I can take the information and directly deposit it into memory, saving a lot of time that the CPU would have done that. The CPU can go do something else more important or equally as important as getting the data into memory. So here we have DMA controllers, manage data transfers between devices and memory. CPU offloading, DMA performs bulk data movement, reduces CPU overhead, higher data transfer efficiency. Okay, obviously, since I'm basically doing this without having to bother the CPU to get it, it's basically more efficient and better overall system performances. Key takeaways here, effective device and I/O management ensures the right resources are available, data is moved efficiently, and the system remains responsive and reliable. Our goal is to learn how the operating system manages devices and I/O operations to deliver fast, reliable, and efficient services. That's our goal in everything we've basically been talking about, to make things run smoothly. Okay, and then we have device drivers, I/O drivers, any kind of information. Think of whenever you buy yourself a new printer, okay? I think we kind of talked about this a little bit before, in that once we have a device, okay, we have to interface between the device and the operating system. The drivers are the software components that act as the translators between the OS and hardware. The hardware is sending a interrupt. Okay. That interrupt for this particular device has a certain topology. Okay. So with that, okay, there has to be a program that recognizes what that particular printer model is asking for. So those are the drivers. When you get a new piece of hardware, there's a device driver that comes with it. Okay. That's loaded. It has the communications that lets it talk to the operating system. And because there are different devices, okay, different models, different companies, okay, the drivers that are needed in order to interface with the operating system are different. So again, depending on what the particular device you're using. Okay, the key concepts here: driver responsibilities. Initialize devices, handle I/O requests, manage data transfer, hardware abstractions, another concept. Drivers hide device-specific details and present a consistent interface to the operating system. Again, so anything that's specific that really is not going to needs to be handled by the operating system, that is hidden. So you don't need to do it. Okay. My fat fingers are working again. Okay. Okay. And kernel interaction, drivers run in the kernel mode and use system calls and interrupts to interact with the operating system. Okay, remember we had a user mode and kernel mode, and the user side basically did calls. The kernel side was the where we actually did all the work. Okay, so kernel interaction. Okay. Examples: printer drivers, display drivers, network drivers. Okay, same sort of thing. Even though we're talking about different types of hardware, that hardware has a certain uh, I guess you could say a certain way that needs to be communicated with. Okay. Okay. The specifics of if I'm this printer, this is what I'm needing. So those are displayed with the drivers. Okay. Buffering and caching and spooling. Okay. Buffering temporary memory areas hold data while it's being transferred from a device. So basically, I'm buffering up, okay, so that I'm not waiting for every hardware cycle to occur to send me data. I'm basically getting data in advance. And while I'm getting that data in advance, I'm taking that and putting it in a memory or storage location so that I'm actually just reading ahead. Okay, that's what the buffer does. I'm getting a temporary memory where I'm reading ahead, saving data, so that when I really need the data, I don't have to go out to the hard drive. Okay, cache memory stores efficiently use data for faster future access and reduce I/O. Okay. Similar to buffering. Okay, stores a frequent and used data for faster future access. Whereas buffering, basically, we're looking to, kind of put things ahead of time. Caching is saying that if I'm going to need something frequently, okay, if I'm not really buffering to get the head, but I'm going to need this data frequently. So I'm going to need it now, and I know I'm going to need it, 10 seconds from now and 20 seconds from that. Then if I know that I'm going to need it, rather than writing it out to the memory one time and then, having to go back to a hard drive in order to get more memory or get more data to put into memory, this has a cache, and it says this cache that I'm producing is saying that I'm going to use this often. And so I'm not going to write it back out to the disk. I'm going to keep it close by so I can get to it quickly. That's our caching. Spooling, simultaneous peripheral operations online. Okay. Uses disk as a queue to manage I/O requests. For example, print jobs. We'll spool the print for the print job. Notice that this spooling happens on its own. This spooling is basically taking information from the operating system or from memory and making that available to the I/O device without having to have any kind of special processing by the central processing unit. Similar to the DMA reversed. Okay. It's getting data from memory and giving it to the hardware device in advance. Okay, in advance. It doesn't need the CPU in order to do that. The spooling operation itself does that. Benefit: reduces waiting time, increases throughput, better utilizes the system. Disk scheduling algorithms. Okay, disk scheduling algorithms determines the order in which pending I/O requests are served. As far as what comes first and what comes second. The routines are, first come, first serve. Yeah, that's the priority. Next one is SSTF, shortest seek time first. Okay, selects the request closest to the current head position, reduces seek time. Scan, elevator algorithm. This head moves in one direction, serving requests until the end, and then reverses. So I'm looking and scanning for data, anything that's in front of me. Okay. I'm not looking at it now and then skipping behind me to see if I can find it and skipping in front of me to see if I can find it. Scanning alert says I'm only going in one direction. Once I get to the end, then I start going through the opposite direction. Okay, but I'm only looking for stuff that I'm going to hit in the future. Excuse me. C-scan, circular scan, head moves in one direction only. After reaching the end, it jumps back to the beginning without servicing requests on the return. So instead of going forward, getting to the end, and then automatically turning around and going the other way, this one says I'm going to go to the end, and then once I hit the end, I'm going to start back at the beginning and then go again. So a little different between the C-scan and the regular scan as far as when I'm trying to find information. Okay, practical applications, storage devices, SSD, HDD, for higher performance, USB devices, network adapters, modern storage systems, all are practical applications of devices and I/O management that has to be put in place depending on what the particular device is. So our key takeaways: device drivers bridge hardware and the operating system by buffering, by caching, by spooling, and by disk scheduling techniques. The goal is to understand how the operating system manages device drivers and I/O operations to ensure efficient communication. Okay, so we've gone through processors, we've gone through memory, now we've gone through I/O devices, and we have looked at the three main areas that that the operating system is going to be involved in. Okay, so with that, week 4, we'll jump into week 5. Again, looking at your high level, look at what we talked about here as far as what was discussed. Be ready for a small quiz on this Tuesday. Okay. Any questions, let me know. With that, we're going to call it a day and have a good day, and we'll see you on Tuesday. Bye.